Think back to your high school or college physics class. Do you remember Ohm's law? It's about electricity, voltage, current, resistance. That's what I want to talk about, the electrical resistance of the ground. But resistance varies with the size of the resistor, which isn't really helpful when you're trying to map a large area. So we use resistivity, which takes into account the geometry of the measurement. Essentially, what we do is hook up a battery between two metal stakes we drive into the ground to create an electric field. Then we measure the voltage from two other stakes, do a simple little calculation, and come up with resistivity. Occasionally, we compete with other practitioners. Now, it's true, resistivity is remote sensing. It uses a black box. But it is based on actual physical principles with reproducible results. When we do resistivity measurements, we inject electricity into the ground. We try very hard not to shock people or animals, though it does occasionally happen. We're not the only ones in an agricultural setting to create pulsed electric fields. This means we have to avoid areas with electric fences and buried power lines and pipes and such. I have been told that there's a similar setup that's used to drive earthworms up to the ground surface. Although in all my days, I have never noticed any unusual animal behavior associated with any of our electrodes. And we have been doing resistivity surveys at the State Geological Survey for over 80 years now. In that time, we've used many different types of field equipment, many variations in portability. Today, we use digital instruments with multiple receiving channels that can switch over hundreds of measurements on an array of electrodes so that we can produce a 2D image of the subsurface. Resistivity is sensitive to several different and useful properties. For instance, we often take advantage of the contrast in resistivity between clay, which has a low resistivity, and sand, which has a higher resistivity. Resistivity was initially used to locate mineral deposits because it's very sensitive to the ionic content of groundwater. This graph, for instance, shows a strong relationship between chloride concentration and resistivity. This property is extremely useful for many environmental applications where one might want to trace a leachate plume. Here's an example at a landfill in northern Illinois. When a dead body decomposes in the ground, it produces some really nasty juices that are highly conductive. One might be able to locate that body by mapping those fluids. Resistivity is especially good at locating water-bearing sand and gravel deposits buried within glacial till. This is our bread and butter application at the State Geological Survey for water resource mapping through the years. The product of a 2D profiling is an electrical model of the subsurface. For instance, in these ridges, we can image the sand shown here in warm colors and distinguish it from clay in the cooler colors. Resistivity is a well-known application for exploration of archaeological sites, looking for hearths and foundations, walls, implements, all which have a different resistivity from the surrounding soils. Combining resistivity images with images from other geophysical methods, such as seismic reflection profiling, which we show here, is a new way to get more bang for your buck from your geophysics budget. With our new high-speed receivers, we're able to tow a resistivity cable in the water from a boat, and thereby acquire continuous profiles of sub-bottom sediments. Electromagnetic induction is a variation on resistivity that can be done from the air. Airborne surveys have the potential to provide us with 3D images of the subsurface. So in this talk, I've only really scratched the surface of possible applications for resistivity. Maybe you can think of some ways that resistivity could be used in your research. If so, let me know and we'll get together a collaboration. Thank you.